Picture a scene where entire galaxies, colossal islands of stars, gas, and dust drift toward one another in the vast, silent expanse of space, not as strangers passing in the night, but as cosmic partners drawn together by an invisible force, destined to collide in a spectacle of unimaginable scale. This isn't science fiction. It's happening right now in the depths of the universe, where galaxies engage in a slow, majestic dance that unfolds over hundreds of millions of years. And what emerges from these collisions, not destruction, but transformation, a rebirth of stellar landscapes that defy our wildest imaginations. What if I told you that our own Milky Way is part of this cosmic choreography? In about 4 billion years, it will meet its neighboring galaxy, Andromeda, in a collision so colossal it will reshape the night sky forever. But this isn't just a distant future event. It's a window into the universe's grandest artistic performances. Galactic collisions are where chaos and beauty intertwine, where gravity sculpts new forms from the wreckage, and where the universe reveals its most dramatic secrets. These encounters aren't rare accidents. They're fundamental to how galaxies evolve, grow, and even give birth to new generations of stars. So what really happens when galaxies collide? It's not the cataclysmic crash you might expect. Instead, think of it as a gravitational tango, a slow, intricate interplay where stars, though countless in number, rarely touch. The real drama unfolds in the invisible forces at work. Tidal tails of gas stretched like cosmic taffy, shockwaves triggering stellar nurseries, and black holes lurking at the hearts of galaxies, destined to merge in a crescendo of energy. These collisions paint the cosmos with some of its most breathtaking sights, from the Antennae galaxies, with their starry arcs, to the mice galaxies, racing through space, trailing streams of newborn stars. This is the universe's way of reinventing itself, and today we're going to unravel the science behind these celestial masterpieces. By the end of this journey, you'll never look at the night sky the same way again. To understand the cosmic ballet of colliding galaxies, we need to start with the silent conductor of this grand performance, gravity. It's the fundamental force that orchestrates every move, pulling galaxies toward one another across millions of light years. But here's the twist. While gravity brings them together, the sheer vastness of space means these collisions play out in slow motion, over timescales that dwarf human history. Picture two immense crowds of stars passing through one another, their individual members so far apart that direct collisions are almost unheard of. The real drama isn't in stars crashing, it's in how gravity bends and twists the galaxies themselves, sculpting them into entirely new forms. Take the iconic Antennae galaxies, for example. These two spiral galaxies have spent hundreds of millions of years in a gravitational embrace, their long, luminous tails stretching across space like celestial brushstrokes. Those tidal tails aren't just beautiful, they're cosmic breadcrumbs, revealing how gravity strips gas and stars from the galaxy's outer edges, flinging them into space. Meanwhile, deep within the collision zone, shockwaves compress vast clouds of gas, igniting bursts of star formation so intense they outshine entire galaxies. This is where the universe's recycling program shines. Old gas clouds collapse into new stars, and the galactic wreckage becomes a nursery for the next generation. But gravity doesn't just reshape galaxies, it also stirs up the supermassive black holes lurking at their cores. As galaxies merge, their central black holes begin a spiraling dance, eventually crashing together in a cataclysmic event that sends ripples through space-time itself. These mergers are so powerful they release energy in the form of gravitational waves, a phenomenon predicted by Einstein and now observed by astronomers. It's a reminder that galactic collisions aren't just about what we see, they're about the invisible forces rewriting the rules of the cosmos. What's truly astonishing is how these collisions follow a cosmic script written by physics. Computer simulations let astronomers rewind and fast-forward these events, revealing patterns that match what we observe in the real universe. From the delicate mice galaxies with their trailing tails to the chaotic beauty of the Cartwheel galaxy, each collision tells a unique story of transformation. And by studying them, we're not just decoding the fate of distant galaxies, we're glimpsing the future of our own Milky Way, destined to merge with Andromeda in a spectacle that will redefine the night sky. These collisions aren't endpoints, they're turning points in the life story of galaxies, where destruction gives way to rebirth on a scale we're only beginning to comprehend. Galactic collisions may seem like violent, chaotic events, but they follow a cosmic playbook, with each encounter unfolding in its own distinct way. Think of it like a dance. Sometimes two partners merge into one, while other times they swing past each other, forever changed by the encounter. The outcome depends on the size, speed, and angle of the galaxies involved, creating a stunning variety of cosmic transformations. Take major mergers, for instance the ultimate galactic showdowns where two galaxies of similar size, like the Milky Way and Andromeda, spiral toward each other in a slow-motion embrace. These collisions are rare, but when they happen, they rewrite the rulebook. Gravity stretches and distorts their shapes, flinging stars and gas into sweeping tidal tails that glow with newborn stars. Over billions of years, the two galaxies lose their original forms entirely, merging into a single, larger galaxy, often an elliptical one, smooth and featureless compared to the spirals they once were. This is the fate awaiting our Milky Way, destined to blend with Andromeda into a brand new cosmic structure some call Milkdromeda. But not all collisions are so dramatic. Minor mergers happen when a massive galaxy, like our own, absorbs a much smaller one. Think of a giant swallowing a dwarf. These events are far more common, and they leave subtler fingerprints. The smaller galaxy gets torn apart by tidal forces, its stars scattered into a faint halo around the larger one. Our Milky Way has done this countless times, with remnants of past meals still visible as streams of stars arcing across the sky. The Sagittarius dwarf galaxy, for example, is currently being pulled apart in this very way, its stars slowly dissolving into the Milky Way's outer reaches. Then there are the near-misses galaxies that don't fully merge but pass close enough to warp each other's shapes. These gravitational encounters can create some of the most bizarre and beautiful structures in the universe. The Cartwheel galaxy, for instance, looks like a cosmic bullseye, its ring-like structure the result of a smaller galaxy punching straight through its center, sending shockwaves rippling outward like a stone dropped in water. Other galaxies end up with long, whip-like tails or bizarre, lopsided arms, all sculpted by the delicate tug of gravity. The universe is full of these celestial interactions, each leaving behind unique signatures for astronomers to decode. Some collisions trigger frenzies of starbirth, lighting up galactic cores with brilliant blue clusters. Others funnel gas towards supermassive black holes, igniting them into blazing quasars. And in rare cases, galaxies can even pass through one another like ghosts, their stars so spread out that they emerge nearly unscathed. Every collision tells a story, a chapter in the life cycle of galaxies, where destruction and creation go hand in hand. Hidden in the shadows of every galactic collision is an unseen maestro dark matter. This mysterious substance, invisible to telescopes yet outweighing all the stars and gas in a galaxy combined. is the silent architect shaping how galaxies collide and merge. While we can't see it directly, its gravitational fingerprints are everywhere, orchestrating the cosmic dance from behind the curtains. Imagine two galaxies approaching each other not as isolated collections of stars, but as vast clouds of dark matter, their invisible halos stretching far beyond the luminous edges we observe. These halos act like gravitational scaffolds, determining the speed, angle, and ultimate fate of the encounter. Computer simulations reveal just how pivotal dark matter is in these collisions. When galaxies interact, their dark matter halos intertwine first, creating a gravitational framework that pulls the visible stars and gas into alignment. Without this unseen influence, galaxies would pass through each other like ghosts, their stars too spread out to collide. But dark matter's relentless tug slows them down, ensuring they eventually merge. It's why we see such spectacular tidal tails and warped shapes. The visible matter is just tracing the contours of an invisible battlefield. The role of dark matter becomes even more striking when we compare predictions to real-world observations. Take the famous Bullet cluster, where two galaxy clusters collided in a way that separated their dark matter from their gas. The gas, slowed by friction, lagged behind, while the dark matter, detected only by its gravitational lensing effect, plowed ahead. This cosmic snapshot proved dark matter isn't just a theory, it's the backbone holding these collisions together. And here's the twist: dark matter doesn't just guide galaxies, it preserves them. During a merger, stars are often flung far from their original homes, yet they remain bound to the new galaxy by the dark matter halo's immense gravity. This invisible glue ensures that even the most violent collisions don't tear galaxies apart entirely. Instead, dark matter weaves the wreckage into something new, a testament to its role as the universe's ultimate sculptor. So the next time you gaze at an image of colliding galaxies, remember, the beauty we see is just the surface. The real story unfolds in the dark, where an unseen force molds the cosmos, one merger at a time. Among the countless galactic collisions unfolding across the universe, a few stand out as cosmic celebrities, celestial landmarks that have reshaped our understanding of how galaxies evolve. The Antennae galaxies, officially known as NGC 4338 and NGC 4339, are perhaps the most iconic. Located about 45 million light-years away, these two spiral galaxies have been locked in a gravitational embrace for the past 300 million years. Their nickname comes from the twin tidal tails stretching outward, each spanning hundreds of thousands of light-years, like the delicate filaments of an insect's antennae. But these structures aren't just beautiful, they're cosmic laboratories. Within those luminous arcs, shockwaves from the collision compress vast clouds of gas, igniting some of the most intense star-forming regions ever observed. The antennae are a snapshot of chaos and creation, where gravity's relentless pull transforms two orderly spirals into a single, dazzling mess of newborn stars and swirling dust. Then there are the mice galaxies, another pair caught in a dramatic pas-de-deux. Officially named NGC 4672 and NGC 4673, these galaxies are separated by about 160,000 light-years, but connected by a bridge of stars and gas, a cosmic umbilical cord forged by gravity. Their long, streaming tails, each stretching nearly 500,000 light-years, reveal the sheer power of tidal forces. Unlike the antennae, which are further along in their merger, the mice offer a glimpse into an earlier stage of collision, where galaxies are still distinct but irrevocably altered. Astronomers study these elongated shapes like forensic scientists, piecing together the trajectory and speed of the encounter from the debris left behind. But not all famous collisions are between equals. Take the Cartwheel Galaxy, a bizarre ring-shaped structure that looks like it was struck by a celestial bullet. In reality, a smaller galaxy punched straight through its center millions of years ago, sending shockwaves rippling outward. The result, a galaxy reborn with a brilliant outer ring of young, blue stars and a quieter core of older stars, a bullseye painted across the cosmos. Meanwhile, the Tadpole Galaxy, with its long, star-studded tail, tells a story of a near miss where a smaller intruder grazed its edge, yanking a stream of stars into space like taffy. These collisions aren't just awe-inspiring sights, they're time capsules. Each one represents a different chapter in the life cycle of galaxies, from first contact to final merger. By studying them, astronomers have pieced together a cosmic playbook, predicting how galaxies like our Milky Way will change over billions of years. And with every new telescope image, we uncover more details: hidden black holes, rogue star clusters, and even the faint glow of dark matter, all whispering secrets about how the universe builds, destroys, and rebuilds itself on the grandest scales. Right now, Andromeda is hurtling toward us at 250,000 miles per hour, a speed that would cross the entire United States in just 10 seconds. Yet despite this breakneck pace, the collision with our Milky Way won't happen for another 4.5 billion years. Time moves differently on cosmic scales, and what feels like an inevitable crash is really more of a slow-motion tango, choreographed by gravity over epochs. When the two galaxies finally meet, the first thing to understand is this: space is so vast that actual collisions between stars are almost impossible. The average distance between stars in a galaxy is about 4 light-years, that's 25 trillion miles. So while Andromeda's trillion stars and the Milky Way's 300 billion will intermingle, they'll mostly glide past one another like ships in the night. The real drama unfolds in the gravitational tides, where invisible forces will twist and stretch both galaxies into entirely new shapes. Picture the night sky 4 billion years from now. As Andromeda approaches, it'll grow from a faint smudge to a brilliant, sprawling disk, eventually spanning half the sky. Then, over millions of years, tidal forces will start pulling long, shimmering streams of stars from both galaxies, creating luminous bridges and loops visible even to the naked eye. The cores of the Milky Way and Andromeda, each harboring a supermassive black hole, will begin a spiraling dance, circling each other for millions of years before finally merging in a titanic burst of gravitational waves. The end result, a colossal elliptical galaxy nicknamed Milkdromeda, will emerge a smooth, golden-hued island of stars without the spiral arms we know today. But don't mistake this for a quiet retirement. The merger will ignite fireworks of star formation as compressed gas clouds collapse into newborn stars, while older stars are flung into chaotic new orbits. Our solar system, if it still exists, might find itself hurled into the galactic suburbs or even ejected into intergalactic space. What's truly mind-bending is that this future collision isn't just speculation. Astronomers have observed similar mergers across the universe, and supercomputer simulations map out every stage with stunning precision. We're seeing the Milky Way's fate written in the stars of other galaxies, a reminder that even the cosmos is in constant flux, rewriting itself in cycles of destruction and rebirth. Among the most breathtaking sights in the universe are starburst galaxies, cosmic fireworks unleashed when galaxies collide. Picture a celestial pressure cooker where vast clouds of gas and dust, squeezed by gravitational forces, ignite into frenzied nurseries of newborn stars. These starburst regions can produce stars hundreds, even thousands of times faster than ordinary galaxies, turning quiet cosmic neighborhoods into dazzling hubs of stellar birth. The Tadpole Galaxy is a stunning example of this phenomenon. Its long, luminous tail, stretching 280,000 light-years across space, isn't just a trail of destruction, it's a ribbon of creation. As the galaxy interacted with a smaller intruder, tidal forces ripped streams of gas from its body, compressing them into dense knots where gravity took over. Now that tail glows with the blue-hot light of countless young stars, each one a testament to the transformative power of collision. But the tadpole isn't alone. The Cigar Galaxy, officially known as Messier 82, is another starburst superstar, its core so packed with newborn stars that it outshines the entire Milky Way in infrared light. What makes these galaxies so prolific? It all comes down to the physics of chaos. When galaxies collide, their gas clouds don't just drift passively, they slam together like ocean waves, creating shock waves that trigger collapse. Imagine a giant cosmic hand crumpling a sheet of paper. Every fold and crease becomes a pocket where gas condenses, heats up, and eventually ignites into stars. These starburst episodes are short-lived by cosmic standards, often lasting just a few tens of millions of years, but in that time, they can reshape an entire galaxy's destiny. The aftermath is just as fascinating. Starburst galaxies eventually exhaust their gas reserves, leaving behind a glittering legacy of star clusters and supernova remnants. Some, like the nearby Messier 83, showcase intricate spiral patterns woven by successive bursts of star formation, each wave leaving its mark like rings in a tree trunk. Others, like the irregular galaxy IC10, reveal how starbursts can defy galactic norms, turning orderly structures into vibrant, chaotic tapestries. These cosmic firework displays aren't just beautiful, they're vital clues to understanding how galaxies grow and evolve. By studying starbursts, astronomers piece together the life cycles of galaxies, from their explosive births to their quiet twilight years. And as telescopes peer deeper into the universe, uncovering starburst galaxies in the distant, early cosmos, we're witnessing the universe's most creative eras, where chaos doesn't just destroy but builds anew. Deep in the heart of every galaxy, hidden behind swirling veils of dust and stars, lies a gravitational monster, a supermassive black hole. These cosmic behemoths, weighing millions or even billions of times the mass of our Sun, are the silent rulers of their galactic domains. But when galaxies collide, something extraordinary happens. These titans are forced out of solitude, drawn into a dance that will end in one of the most violent events in the universe. Imagine two supermassive black holes, each the anchor of its own galaxy, suddenly finding themselves on a collision course. As their host galaxies merge, the black holes begin a spiraling descent toward one another, locked in a gravitational embrace that can last for hundreds of millions of years. During this time, they form what astronomers call a binary black hole system, a pair of unimaginably dense objects orbiting a shared center, warping spacetime itself with their immense gravity. The space around these duos is anything but quiet. As they circle each other, they stir up the surrounding gas and dust, heating it to millions of degrees and creating some of the most luminous objects in the cosmos, active galactic nuclei. These blazing cores can outshine all the stars in their galaxies combined, spewing jets of high-energy particles that stretch across thousands of light years. In some cases, the black hole's gravitational tug of war flings stars away at incredible speeds, creating hypervelocity stars that race through intergalactic space like cosmic outcasts. But the most dramatic moment comes when the black holes finally merge. As they inch closer, their orbits tighten, and they begin losing energy in the form of gravitational waves, ripples in space-time predicted by Einstein over a century ago. In the final seconds before collision, these waves crescendo into a cosmic symphony, releasing more energy than all the stars in the observable universe combined. The resulting shockwave distorts spacetime itself, leaving behind a single, even more massive black hole, a silent testament to the galaxy-shattering event that created it. We've only recently gained the tools to witness these phenomena firsthand. Gravitational wave detectors like LIGO and Virgo have begun picking up the echoes of smaller black hole mergers, while telescopes like Chandra and Hubble capture the blazing light shows from binary systems. Each observation peels back another layer of mystery, revealing how these colossal encounters shape the galaxies we see today. And somewhere in the distant future, the supermassive black holes at the centers of the Milky Way and Andromeda will write their own final chapter, a collision that will send ripples across the cosmos and redefine our galactic home forever. One of the most breathtaking sights in galactic collisions isn't the chaos at the center. It's the luminous ribbons of stars and gas stretching far into the void, like celestial brushstrokes across the darkness. These are tidal tails, cosmic scars carved by gravity's relentless pull as galaxies graze or merge. Picture two galaxies swinging past each other in a gravitational slingshot, their outer layers stretched and torn like taffy, leaving behind trails that can span hundreds of thousands of light years. The Antennae galaxies showcase this phenomenon perfectly, their twin tails glowing with the blue fire of newborn stars and the faint shimmer of displaced gas. But these structures aren't just beautiful accidents, they're forensic evidence, telling astronomers exactly how the collision unfolded. What makes tidal tails so special is their composition. Unlike the dense cores of galaxies, these streams are gossamer thin, a delicate mix of orphan stars, rogue star clusters, and vast clouds of interstellar material. As gravity yanks them outward, shockwaves ripple through the gas, triggering bursts of star formation. The result, tidal tails often glitter with young, hot stars, stellar infants born from the violence of the collision itself. In the tadpole galaxy's 300,000 light-year long tail, for example, astronomers have spotted superstar clusters, each one a dazzling metropolis of stars packed tighter than in our entire solar neighborhood. But tidal tails don't just create, they preserve. Like cosmic time capsules, they trap stars and gas in trajectories that reveal the collision's history. By mapping their curves and densities, scientists can rewind the encounter, calculating the galaxy's original speeds, angles, and even their masses. Some tails, like those of the mice galaxies, act as gravitational breadcrumbs, tracing paths that show how the galaxies will eventually loop back toward each other for another pass. Others, like the faint streams around the Milky Way, are the ghostly remnants of ancient mergers, proof that our galaxy has been cannibalizing smaller neighbors for billions of years. Perhaps most astonishing is how long these structures endure. Tidal tails can persist for billions of years, far outliving the collisions that birthed them. They become intergalactic waypoints, marking where galaxies once met and transformed each other forever. And as telescopes peer deeper into the universe, uncovering even more distant examples, we're learning that these luminous scars aren't just side effects, they're fundamental to how galaxies grow, recycle material, and seed the cosmos with new generations of stars. In the grand tapestry of galactic evolution, tidal tails are both the threads and the needles, weaving together the story of how the universe reshapes itself. Among the most striking cosmic artworks born from galactic collisions are ring galaxies, structures so perfectly symmetrical they seem sculpted by an invisible hand. These rare and mesmerizing formations occur when a smaller galaxy, like a celestial bullet, punches straight through the center of a larger spiral galaxy. The impact sends shockwaves rippling outward through the galactic disk, compressing gas and dust in a circular wave that ignites a brilliant ring of newborn stars. The Cartwheel Galaxy, located 500 million light-years away in the constellation Sculptor, is the poster child for this phenomenon. Its vibrant blue outer ring, dotted with star-forming regions, contrasts starkly with its older, yellower core, a visual timeline of the collision that reshaped it. What makes ring galaxies so fascinating is the precision of their formation. Unlike the chaotic tangles of most mergers, these collisions create near-perfect geometric shapes. As the intruder galaxy plows through the center, its gravitational pull disrupts the larger galaxy's structure, flinging stars outward in a radial pattern while leaving the core relatively undisturbed. The resulting shockwave acts like a pebble dropped in a pond, triggering star formation in an expanding circle that can persist for hundreds of millions of years. The Hoag's object galaxy takes this elegance even further, with a nearly flawless ring orbiting a spherical core. Though its origins remain debated, some astronomers suspect a past collision, while others propose intricate gravitational instabilities. But ring galaxies aren't just cosmic oddities, they're laboratories for studying stellar evolution. The Cartwheel's ring, for example, is a hotbed of supermassive star clusters, some containing thousands of stars packed into regions smaller than our solar system. These clusters form under extreme conditions, offering clues about how the universe's most massive stars are born. Meanwhile, the galaxy's faint spokes, filaments of dust and gas connecting the ring to the core, hint at the delicate balance between destruction and creation. As the ring expands, it leaves behind pockets of gas that collapse into new stars, while older stars are scattered into the galaxy's outer reaches. The lifespan of these galactic ripples is surprisingly long. Even after the intruder galaxy has moved on, the ring continues to evolve, its stars aging and its structure slowly dispersing. Some rings, like that of the AM064474 galaxy, show multiple concentric circles, suggesting several waves of star formation triggered by the same collision. Others, like the less famous but equally stunning Lindsay-Shapley ring, display warped or incomplete rings, remnants of off-center impacts that didn't strike the bullseye. Each variation tells a different story about the speed, angle, and mass of the colliding galaxies. What's truly remarkable is how these collisions echo across cosmic time. The Cartwheel Galaxy's ring, now 750 million years into its expansion, still glows with the energy of its rebirth. Meanwhile, telescopes like Hubble and JWST have spotted even more distant ring galaxies, their light reaching us from eras when the universe was younger, proving that this delicate dance of destruction and creation has been shaping galaxies for billions of years. In the grand tapestry of cosmic evolution, ring galaxies are rare but radiant stitches, brief, brilliant moments where violence and beauty collide. Hidden behind thick curtains of cosmic dust, some colliding galaxies transform into the universe's most radiant powerhouses, ultra-luminous infrared galaxies, or ULR. These colossal engines of energy don't blaze across the cosmos in visible light like typical galaxies. Instead, they glow fiercely in the infrared spectrum, their brilliance trapped behind dense clouds of dust and gas. The reason when galaxies merge, their interstellar materials collide, triggering frenzied bursts of star formation so intense they outshine entire galaxies. But all that newborn starlight gets absorbed by the surrounding dust, which heats up and re-emits the energy as infrared radiation, a cosmic fingerprint of hidden violence. Take ARP 220, one of the most studied ULR, located 250 million light-years away. At first glance, it might look like a chaotic mess, two spiral galaxies locked in a gravitational death grip. But peer deeper and you'll find a staggering secret. This single object radiates as much energy as 1 trillion suns, nearly all of it pouring out as infrared light. The dust is so thick that visible light telescopes see almost nothing, while infrared observatories reveal a maelstrom of activity. Vast starburst regions churn out new stars at a rate hundreds of times faster than the Milky Way, while twin supermassive black holes, each weighing over 150 million solar masses, lurk at its heart, feasting on the chaos. What makes ULERG so extraordinary is their role as cosmic recyclers. The same dust that obscures their brilliance also acts as a stellar nursery, compressing gas into dense knots where gravity takes over. These galaxies are essentially turning their own wreckage into new stars at breakneck speed, creating dazzling clusters that outshine anything in our galactic neighborhood. And because they're often the result of major mergers, their structures are wildly distorted. Some sport multiple nuclei, remnants of the original galaxy's cores, while others eject colossal winds of gas, driven by the combined energy of supernova and black hole jets. But ULERG aren't just local oddities. In the distant universe, they were far more common, dominating an era when galaxy collisions were frequent. Some astronomers believe these infrared powerhouses are the ancestors of today's giant elliptical galaxies, their furious star formation eventually exhausting the gas supply and leaving behind a quiet, aging giant. Others think they're the birthplaces of quasars, their shrouded black holes eventually clearing the dust to reveal unimaginable brilliance. Either way, ULERG remind us that the universe's most dramatic transformations often happen behind the scenes, hidden from view until the right technology like infrared telescopes pulls back the curtain. The next generation of observatories, like the James Webb Space Telescope, is poised to uncover even more about these enigmatic objects. By peering through their dusty veils, we're not just solving a cosmic mystery, we're witnessing the universe's way of turning chaos into light, one collision at a time. Gas is the unsung hero of galactic collisions, the invisible sculptor shaping the universe's most dazzling spectacles. While stars steal the spotlight, it's the vast reservoirs of gas between them that truly determine the fate of merging galaxies. Picture two galaxies drifting toward each other, their spiral arms brimming with hydrogen clouds so diffuse they'd make Earth's atmosphere seem dense by comparison. Yet when these wispy giants collide, they unleash fireworks visible across the cosmos. The magic happens because gas behaves unlike stars in a merger. Stars separated by light years mostly glide past one another untouched, but gas clouds, they slam together like ocean waves, compressing under the shock of impact. This sudden squeeze triggers a chain reaction. Atoms crowd closer, temperatures spike, and gravity takes over, collapsing these chaotic clouds into dense knots where nuclear fusion ignites. The result, starburst regions where stars form hundreds of times faster than in quiet galaxies like our Milky Way. The iconic Antennae galaxies showcase this brilliantly, their overlapping cores glowing pink with ionized hydrogen, a telltale sign of gas-turned-stellar nursery. But gas doesn't just birth stars, it also steers the entire merger. Like cosmic puppet strings, gas filaments wrap around colliding galaxies, channeling material toward their centers. This influx can awaken dormant supermassive black holes, feeding them until they blaze as quasars. It also redistributes heavy elements forged in stellar explosions, enriching future generations of stars with the building blocks of planets and life. The mice galaxies demonstrate this beautifully, their long tails not just trails of stars but highways of gas, carrying precious metals away from the collision zone like cosmic conveyor belts. Without gas, mergers would be stellar ghost towns, dark, quiet affairs where galaxies simply reshuffled their stars. It's the gas that paints these collisions in vivid color, from the blue hues of young star clusters to the crimson glow of ionized hydrogen. And as telescopes peer deeper into the universe, they're finding that gas-rich mergers dominated the cosmos's youth, turning the early universe into a fireworks display of starbirth. These collisions weren't just destructive, they were the universe's way of recycling, reinventing, and ultimately creating the galaxies we marvel at today. To truly grasp the cosmic dance of colliding galaxies, we need eyes that can peer not just across space but through time itself, and that's where supercomputer simulations come in. These digital laboratories let astronomers rewind and fast-forward galactic collisions over billions of years, revealing secrets no telescope could capture. Imagine watching two galaxies merge in seconds rather than eons, with every star, gas cloud, and wisp of dark matter choreographed by the unbreakable laws of physics. These simulations aren't just animations, they're cosmic time machines built on equations so precise they can predict the fate of our own Milky Way. One of the most groundbreaking revelations from these virtual experiments is how dark matter shapes every merger. In simulations, galaxies arrive wrapped in vast, invisible halos of this mysterious substance, halos that interact long before the visible stars ever meet. As the dark matter tangles, it creates a gravitational scaffold that drags the gas and stars into alignment, warping spiral arms into tidal tails and funneling material toward the galaxy's hearts. Without dark matter's invisible hand, galaxies would pass through each other like phantoms, their stars too sparse to collide. But the simulations show its pull is relentless, ensuring mergers proceed even when the visible evidence seems subtle. Gas, too, plays a starring role in these digital recreations. Supercomputers reveal how colliding gas clouds don't just crash, they ripple with shockwaves that trigger stellar baby booms. The famous Antennae Galaxies simulation, for instance, shows gas compressed into glowing knots where new stars ignite, matching Hubble's real-world images down to the finest detail. Other simulations, like those of the Milky Way and Andromeda's future merger, predict how their gas will light up with starbursts, painting the night sky of any future Earth with unfamiliar constellations. But perhaps the most astonishing simulations focus on supermassive black holes. As galaxies merge, their central black holes spiral toward each other, trapped in a gravitational waltz that can last millions of years. Supercomputers track this dance with breathtaking precision, showing how the black holes fling stars away like cosmic slingshots before finally colliding in a burst of gravitational waves. These simulations even helped astronomers interpret real-world data, like the first ever detection of gravitational waves from black hole mergers, a triumph of virtual science guiding real discovery. The magic lies in how these simulations evolve. Astronomers seed them with initial conditions, galaxy masses, speeds, angles, and let physics take over. When the results mirror actual telescope observations, like the Cartwheel galaxy's perfect ring or the Mice galaxy's streaming tails, it's proof the underlying science is sound. And when discrepancies arise, they hint at gaps in our knowledge, pushing researchers to refine their models. It's a dialogue between digital and observational astronomy, each informing the other to unravel the universe's grandest collisions. What's truly humbling is realizing these simulations aren't just academic exercises. The fate of our own galaxy is written in their code. By studying thousands of virtual mergers, astronomers confidently predict that the Milky Way and Andromeda will one day blend into an elliptical galaxy, their black holes merging in a finale that will ripple across the cosmos. These digital crystal balls remind us that the universe's most dramatic transformations aren't just happening out there, they're woven into the future of our own galactic home. The Hubble Space Telescope has gifted us more than just stunning cosmic postcards. It's handed scientists a treasure trove of data, transforming our understanding of how galaxies collide. Take the Veil Galaxy, officially known as NGC 2670, for example. Hubble's razor-sharp vision revealed delicate filaments of dust and gas stretching between two merging galaxies, threads so fine they look like cosmic spider silk. These structures aren't just beautiful, they're evidence of gravity's subtle artistry, gently pulling material from one galaxy to another in a slow-motion exchange. Without Hubble's keen eye, we might never have noticed these faint bridges, let alone realized how common they are in galactic collisions. Then there's NGC 6052, a chaotic whirlpool of stars that first appeared to astronomers as a single, misshapen galaxy. Hubble's images sliced through the confusion, revealing it was actually two galaxies caught mid-collision, their spiral arms shredded into a dazzling stellar storm. The clarity of these snapshots let researchers track individual star clusters and measure their ages, proving that mergers trigger waves of star birth in predictable patterns. It's like watching a time lapse of a forest regrowing after a wildfire. Hubble's images capture the universe's resilience, showing how destruction gives way to rebirth. But Hubble's greatest contribution might be its ability to freeze-frame different stages of galactic encounters. The telescope's deep field surveys, which peered across billions of light-years, caught galaxies colliding in the early universe when such events were far more frequent. Comparing these ancient mergers to nearby ones, like the iconic Antennae galaxies, revealed something astonishing. The same physics governs collisions whether they happened 10 billion years ago or are unfolding today. Gravity's playbook hasn't changed, and Hubble's archive is the proof. What makes Hubble's images truly invaluable, though, is how they bridge art and science. A single frame of the Tadpole Galaxy, with its star-studded tail, can inspire a child to become an astronomer while simultaneously helping researchers model how tidal forces strip galaxies of their gas. The telescope's portraits of colliding galaxies aren't just data, they're cosmic stories, each one a chapter in the universe's grand narrative of creation and change. And as Hubble's successors, like the James Webb Space Telescope, build on its legacy, we're reminded that every pixel in those images holds secrets waiting to be decoded. While Hubble showed us the visible beauty of colliding galaxies, the James Webb Space Telescope reveals what lies beneath, unlocking secrets hidden behind veils of cosmic dust. With its infrared vision, Webb acts like an X-ray machine for the universe, penetrating dense clouds that block visible light to expose the fiery hearts of galactic mergers. Where older telescopes saw only darkness, Webb uncovers nurseries of newborn stars blazing in vivid detail, their heat signatures painting a picture of creation we've never seen before. Take the stunning clarity of Webb's image of the Cartwheel galaxy. Hubble's view showed a hazy ring, but Webb's infrared sensors revealed intricate structures within clusters of young stars glowing like embers, their light escaping the dust that would have smothered it in visible wavelength. Even more astonishing, Webb spotted tendrils of warm dust spiraling toward the galaxy's core, evidence of material funneling toward a supermassive black hole, a process previously too obscured to study. This isn't just a sharper image, it's a revelation of how collisions feed galactic monsters, turning them into engines of destruction and rebirth. But Webb's greatest power lies in capturing the invisible forces at work. In merging galaxies like ARP 220, where visible light telescopes see only a dusty blur, Webb's infrared eyes detect vast waves of star formation, entire stellar generations bursting to life in pockets of compressed gas. These regions, invisible to Hubble, radiate intense heat, allowing Webb to map their distribution like a cosmic thermal camera. The telescope has even spotted something unexpected. Some colliding galaxies produce far more young stars in their dusty cores than predicted, suggesting our models of galactic recycling need rewiring. Perhaps most thrilling is Webb's ability to spy on supermassive black hole duos during mergers. In the chaos of colliding galaxies, these invisible giants often hide behind thick dust shields. But Webb's infrared instruments detect the heat from their accretion disks, the swirling rings of doomed matter, revealing pairs of black holes circling each other in a gravitational tango. Some, like those in the galaxy merger EARS 196, blaze so brightly they outshine their host galaxies, offering clues about how these monsters grow to staggering sizes. Webb isn't just showing us galactic collisions, it's decoding their life cycles. By comparing mergers in the distant, early universe to nearby ones, astronomers are piecing together how these events shaped galaxies across cosmic time. And with every new image, Webb peels back another layer of dust, exposing the universe's most dramatic transformations in a light we've never seen. Our galaxy, the Milky Way, might seem like a peaceful cosmic island, but it has a hidden history of celestial feasting. Galactic cannibalism, the process where large galaxies consume smaller ones, isn't just a dramatic cosmic event happening elsewhere. It's how our own galaxy grew to its current size. Picture a cosmic predator, its gravitational pull slowly dismantling smaller neighbors, absorbing their stars, gas, and even dark matter into its sprawling structure. The evidence of this galactic diet is written across the night sky if you know where to look. Right now, the Milky Way is in the middle of a quiet but relentless feast. The Sagittarius dwarf galaxy, a tiny companion orbiting our own, is being stretched into stellar streams by the Milky Way's immense gravity. Imagine a cosmic spiderweb with threads of stars pulled from the dwarf galaxy and strewn across our galactic halo like glittering graffiti. These streams, invisible to the naked eye but detectable through telescopes, trace the path of destruction, a celestial crime scene revealing how gravity tears smaller galaxies apart over billions of years. But Sagittarius isn't the Milky Way's first victim, just the latest. Our galaxy's halo holds the remnants of dozens of past mergers, ghostly echoes of smaller galaxies long since devoured. One of the most famous is the Gaia Enceladus galaxy, a dwarf galaxy that collided with the Milky Way around 10 billion years ago. Its stars now mingle with ours, indistinguishable except to the keenest astronomical detectives. By studying their motions and compositions, astronomers have reconstructed this ancient merger, revealing how it shaped the Milky Way's structure and even triggered waves of star formation. What's fascinating is how gentle this cannibalism can be. Unlike the violent, star-forming collisions between large galaxies, these minor mergers are slow and subtle. Stars from the swallowed galaxy rarely collide with our space is just too vast. Instead, they're gradually dispersed, their orbits reshaped by the Milky Way's gravity until they become just another part of the galactic background. The real casualty is the smaller galaxy's structure, torn apart until nothing remains but a few scattered star clusters and a faint smear of dark matter. Yet these mergers aren't just destructive, they're creative. Every time the Milky Way absorbs a smaller galaxy, it gains fresh gas and dust, fuel for future generations of stars. Some astronomers believe these minor mergers are why our galaxy still forms stars today, long after its initial gas reserves should have been exhausted. And by studying the remnants of past meals, we're piecing together the Milky Way's growth history, learning how it evolved from a modest collection of stars into the grand spiral we call home. The Milky Way's appetite isn't unique. Across the universe, large galaxies grow by consuming smaller ones, a process as natural as rain feeding a river. The Andromeda Galaxy, our future collision partner, shows even clearer signs of galactic cannibalism, its outskirts littered with the shredded remains of past mergers. Even giant elliptical galaxies, smooth and featureless, are thought to be the end result of countless collisions, their original structures erased by eons of cosmic consumption. So the next time you gaze at the Milky Way's band of light stretching across the night sky, remember, you're looking at the legacy of a celestial predator, a galaxy built one bite at a time. And somewhere in that glow are the scattered stars of its former meals, silent witnesses to the universe's endless cycle of destruction and renewal. Here's a comforting thought. When galaxies collide, your morning coffee won't suddenly float away. That's because the vast emptiness of space means solar systems like ours are remarkably safe even during the most dramatic cosmic mergers. Picture two crowds of fireflies passing through each other in the night. The chances of any two insects touching are almost zero. Stars operate on a similar scale, separated by distances so immense that direct collisions are vanishingly rare. Our Sun, along with its planetary entourage, would likely continue its quiet orbit around the Milky Way's center, undisturbed by Andromeda's approaching stars. But don't mistake safety for monotony. The night sky during a galactic collision would transform into something unrecognizable, a celestial light show beyond human imagination. As the Milky Way and Andromeda intertwine, new constellations would emerge, stitched together from stars of both galaxies. The familiar band of our home galaxy would warp and distort, replaced by shimmering bridges and loops of starlight. Nebulae, those glowing clouds where stars are born, would ignite like fireworks as colliding gas clouds compress and ignite. Imagine stepping outside to a sky where Andromeda's disk stretches from horizon to horizon, its spiral arms glowing so brightly they cast faint shadows on Earth. Over millions of years, this spectacle would evolve, with tidal streams of stars painting ever-changing patterns overhead. What about planets? Their orbits around their host stars would remain stable, but their cosmic neighborhoods might get a shake-up. Some stars passing relatively close by within a light year or so could nudge comets from the outer solar system, sending them spiraling inward in a celestial pinball game. Earth's night sky might occasionally blaze with new comets, their tails arcing like celestial brushstrokes. Meanwhile, the increased density of stars could mean more nearby supernovae, their brilliant explosions briefly outshining the moon. The real cosmic drama would unfold for civilizations like ours, should they survive billions of years into the future. As the galaxies merge, the night sky's navigational landmarks, the North Star, Orion's Belt, the Southern Cross, would drift beyond recognition. Ancient constellations would dissolve, their stories lost to time, replaced by new patterns woven from two galaxies' worth of stars. The Milky Way's tranquil disk would vanish, replaced by the golden haze of an elliptical galaxy, its stars orbiting in chaotic, three-dimensional path. Yet amid this upheaval, life could persist. Planets nestled in the habitable zones of stable stars would remain oases of calm, their climates governed by their suns rather than the galactic chaos overhead. In fact, the merger might enrich these worlds with new resources, as shock waves from colliding gas clouds deliver fresh supplies of water and organic molecules. The universe has a way of balancing destruction with creation, and for solar systems caught in the storm, that could mean emerging on the other side with new cosmic wonders to explore. So while galactic collisions rewrite the heavens on the grandest scales, they leave the small details like our pale blue dot remarkably untouched. It's a reminder that even in a universe of constant change, some things endure: the steady warmth of a star, the orbit of a planet, and the potential for life to gaze upward and marvel at the cosmos's endless reinvention. Galactic collisions are the ultimate cosmic architects, silently reshaping the universe over timescales that dwarf human history. What begins as a graceful spiral, a pinwheel of stars and gas, can transform into something entirely different through the alchemy of mergers. Take the fate of spiral galaxies like our Milky Way. In their pristine state, they're flat, ordered disks where stars trace neat circular orbits. But when two spirals collide, gravity stirs this orderly arrangement into chaos. Stars are flung onto random paths, gas clouds scatter like leaves in a storm, and over billions of years, the galaxy's elegant spiral arms dissolve into a smooth, football-shaped elliptical galaxy. This metamorphosis isn't destruction, it's reinvention. A celestial makeover that explains why elliptical galaxies dominate crowded regions of the universe where collisions are frequent. The secret to this transformation lies in the physics of chaos. During a merger, gravitational forces act like a cosmic whisk, churning a galaxy's stars into a three-dimensional swarm rather than a flat disk. Picture two crowds of dancers merging on a ballroom floor. At first, their movements might follow predictable patterns, but as they intermingle, their paths become erratic, filling the entire space. That's precisely what happens to stars during galactic collisions. The resulting elliptical galaxy has no clear structure, its stars orbiting in all directions like a hive of disoriented bees. The iconic Sombrero Galaxy, with its bulging core and lack of spiral arms, might be the product of such an ancient merger, a relic of a violent past now frozen in time. But mergers don't just reshape galaxies, they rejuvenate them. When gas-rich galaxies collide, their interstellar clouds slam together, triggering starbursts that can outshine entire galaxies. These newborn stars aren't just any stars, they're enriched with heavy elements forged in the explosions of previous generations. Every merger is like a cosmic recycling plant, where the debris of dead stars becomes the building blocks of new ones. The giant elliptical galaxy Messier 87, famous for hosting the first photographed black hole, owes its immense size and golden hue to countless mergers that fed it both stars and the raw materials for stellar birth. Perhaps the most fascinating aspect is how these collisions contribute to galactic diversity. The universe isn't a one-size-fits-all place. It's a tapestry of galaxies ranging from tiny dwarfs to colossal ellipticals, from irregular blobs to majestic spirals. Collisions are the loom that weaves this variety. Minor mergers where a large galaxy absorbs a smaller one can add just a sprinkle of new stars to a galaxy's outer halo. Major mergers like the impending Milky Way Andromeda collision can completely erase a galaxy's identity, blending two spirals into one featureless giant. And sometimes, when conditions are just right, a collision can even give birth to a new spiral as gas settles back into a disk and begins forming stars in orderly arms. This cycle of collision and rebirth isn't just ancient history, it's happening now in our cosmic neighborhood. The Milky Way's distorted outskirts bear the scars of past mergers, while its future collision with Andromeda promises to rewrite our galactic story. Across the universe, telescopes capture galaxies in every stage of this transformation, from the first tentative gravitational encounters to the final blending of two cosmic giants. Each one is a snapshot in a billion-year album, chronicling how the universe constantly reinvents itself through the slow, inexorable dance of gravity. And as we piece together this grand puzzle, we're not just observers, we're witnesses to the process that shaped the galaxies we call home. While gravity takes center stage in galactic collisions, there's an invisible force working behind the scenes, one that twists, guides, and sometimes even resists the cosmic chaos. Magnetic fields, those vast, invisible webs stretching across galaxies, play a surprising role in determining how gas and dust behave when galaxies collide. Unlike the brute force pull of gravity, these fields operate more like cosmic puppet strings, subtly shaping the flow of material in ways that can either spark stellar birth or funnel matter into spectacular jets. Consider what happens when two galaxies' magnetic fields meet during a collision. At first glance, you might expect them to snap like rubber bands or cancel each other out. Instead, they tangle and merge, creating intricate patterns that influence how gas clouds move. In some cases, these fields act like cosmic shock absorbers, slowing down colliding gas clouds just enough to prevent them from rebounding, effectively trapping material where gravity can work its magic. This compression is why some merging galaxies, like the famous Antennae pair, become starburst powerhouses, their magnetic fields helping to squeeze gas into dense knots ripe for star formation. But magnetic fields can also play the opposite role. In galaxies with supermassive black holes, these fields sometimes channel gas into narrow, high-speed jets that shoot far beyond the galaxy's edges. The galaxy Centaurus offers a stunning example. Its collision with a smaller galaxy millions of years ago not only warped its shape but also energized its magnetic fields, which now funnel particles into jets stretching over 1,000,000 light-years. These jets, visible in radio telescopes, glow with synchrotron radiation, a telltale sign of electrons spiraling along magnetic field lines at nearly the speed of light. What's truly fascinating is how these fields leave forensic evidence of their influence. When astronomers study polarized light from colliding galaxies, they can map the orientation of magnetic fields by seeing how the light waves align. These maps reveal how fields strengthen in collision zones, sometimes becoming 10 times more powerful than the Milky Way's own magnetic web. In the merging galaxy NGC 6245, for instance, magnetic fields have wrapped around tidal tails like cosmic ribbons, guiding the flow of gas even as gravity pulls it outward. The universe loves a good paradox, and magnetic fields in galactic collisions deliver just that. They can both nurture and disrupt. While they help birth stars in some regions, they can also stabilize gas clouds elsewhere, preventing them from collapsing. In the Whirlpool galaxy's collision with its smaller companion, magnetic fields near the core are so strong they act like a cosmic trampoline, keeping some gas suspended instead of feeding the central black hole. It's a delicate balance, one that reminds us galaxies aren't just collections of stars, and gas, they're dynamic systems where invisible forces sculpt visible beauty. As telescopes grow more sophisticated, we're beginning to see just how deeply magnetic fields shape galactic evolution. Future observations with instruments like the Square Kilometre Array radio telescope promise to reveal these fields in even greater detail, showing how they weave through colliding galaxies like invisible threads in a tapestry. And with every new discovery, we're learning that the universe's most dramatic transformations aren't just about gravity's pull. They're about the subtle, persistent influence of magnetism, quietly guiding the chaos of cosmic collisions. Some galaxies don't collide head-on, they flirt. The Whirlpool galaxy and its smaller companion, known as NGC 5195, are the perfect cosmic example of this delicate courtship. Separated by about 31 million light-years from Earth, these two galaxies are caught in a mesmerizing gravitational embrace, their shapes slowly warping under each other's influence like dancers pulling each other across a ballroom. The Whirlpool's elegant spiral arms, usually symmetrical and serene, have been stretched into sweeping, distorted arcs by its companion's persistent tug, a preview of the dramatic transformation awaiting both galaxies over the next few 100 million years. What makes interacting pairs like these so fascinating is how they reveal the subtle beginnings of galactic mergers. Unlike full-blown collisions that create fireworks of star formation, these early-stage encounters show gravity's patient craftsmanship. The Whirlpool's companion has already plowed through its disk once, triggering waves of compression that lit up spiral arms with newborn stars. Now, as it loops back around for another pass, it's pulling long filaments of gas and dust from the Whirlpool's outer edges, cosmic threads that may one day form a luminous bridge between them. This slow-motion disruption is how many mergers begin, not with a cataclysmic crash, but with a gradual, gravitational conversation that reshapes both participants. The Whirlpool isn't alone in this celestial waltz. The Mice Galaxies, officially named NGC 4672 and NGC 4673, showcase an even more advanced stage of interaction. Their long, streaming tails, each nearly 500,000 light-years long, are like cosmic breadcrumbs, marking the path of their gravitational dance. These tails don't just trail behind. They're actively forming stars, proving that even in the early phases of a merger, the universe finds ways to create amid the chaos. Meanwhile, the eyes of astronomers turn to systems like ARP 273, where two galaxies brush so close that their shapes become nearly unrecognizable, their spiral arms knotted into bizarre loops and whirls. Interacting pairs teach us that galaxy mergers aren't single events, they're multi-act plays. Some galaxies, like the famous Siamese twins system, may orbit each other for billions of years before finally merging, their gravity gradually sapping each other's momentum. Others might experience a single close pass that alters them forever, then drift apart, forever changed by the encounter. The outcome depends on their speed, angle, and the invisible scaffolding of dark matter that surrounds them. Perhaps the most valuable lesson from these cosmic pairs is how common they are. Telescopes like Hubble have revealed that up to 1 in every 25 galaxies is currently interacting, a reminder that the universe is anything but static. For every grand collision like the Antennae galaxies, there are countless quieter encounters unfolding right now, their slow gravitational whispers reshaping the cosmos one delicate tug at a time. And as we study them, we're not just watching distant events, we're glimpsing the future of our own Milky Way, already shaped by past encounters and destined for another, far grander dance with Andromeda. Among the countless celestial wonders shaped by galactic interactions, few are as breathtaking as the Butterfly Galaxy. Officially catalogued as NGC 6302, this cosmic masterpiece earned its nickname from the vast, wing-like structures of glowing gas that stretch across 3 light-years of space. These delicate filaments aren't just beautiful, they're the remnants of a violent stellar metamorphosis, where a dying star at the galaxy's heart ejected its outer layers in brilliant, symmetrical waves. But here's the twist. This stellar swan song was likely orchestrated by an unseen gravitational partner, a companion star, or even a past galactic encounter that destabilized the system, triggering one of the most dazzling displays in the cosmos. What makes the Butterfly Galaxy so extraordinary is the chemistry etched into its wings. The nebula glows in vivid hues, blues from ionized oxygen, reds from nitrogen, and subtle greens from hydrogen, a palette that reveals the elemental ingredients forged in the star's core and blasted into space. Temperatures in these outflowing gases soar to 36,000 degrees Fahrenheit, hot enough to vaporize diamonds, while the central star itself, now a white dwarf, burns at an unimaginable 400,000 degrees. This isn't just a pretty picture. It's a forensic snapshot of stellar death and rebirth, where expelled material will eventually seed future generations of stars and planets. The butterfly symmetry holds another clue. Such precise, bipolar structures often form when a dying star is part of a binary system or when its surroundings have been shaped by external forces, like the gravitational tides of a passing galaxy. Imagine a cosmic pebble dropped into the still waters of a star's atmosphere, sending ripples of gas outward in near-perfect patterns. Some astronomers suspect the butterfly's wings were sculpted by such an encounter, where a close gravitational interaction, whether with a companion star or a rogue interstellar cloud, channeled the star's ejector into those iconic lobes. This galactic artwork also offers a glimpse into our own solar system's future. Billions of years from now, our sun will undergo a similar transformation, shedding its outer layers in a planetary nebula. But without a gravitational dance partner, its farewell might lack the butterfly's dazzling symmetry, ending instead as a more subdued spherical glow. That contrast underscores how cosmic interactions, whether between stars or entire galaxies, don't just destroy, they create beauty on scales we're only beginning to appreciate. For astronomers, the butterfly galaxy is more than a visual marvel, it's a laboratory. By studying its intricate structures, they're unraveling how gravitational interactions, both large and small, shape the life cycles of stars. And with every new observation from telescopes like Hubble and JWST, we're reminded that even in the cold vastness of space, the universe has an artist's touch, painting its grandest masterpieces with the brushstrokes of chaos and gravity. Long before the Milky Way and Andromeda began their slow-motion dance, the early universe was a cosmic demolition derby, a chaotic era when galaxies collided with astonishing frequency. Picture a time when the cosmos was smaller, denser, and filled with gas-rich building blocks careening into one another like celestial bumper cars. These ancient mergers weren't just more common, they were essential construction sites, assembling the first massive galaxies from smaller fragments in the universe's toddler years. The James Webb Space Telescope has become our time machine to this violent nursery, peering over 13 billion years into the past to catch these primordial crashes in action. One stunning example is the galaxy cluster nicknamed the Sparkler, where Webb spotted tiny proto-galaxies swarming around a larger central galaxy like bees around a hive, each one destined to be absorbed in a series of mergers that will build a giant elliptical galaxy. What's astonishing is how these infant galaxies, barely a billion years old, already show signs of collision-induced star formation, their compact bodies glowing with the blue-hot light of newborn stars. The universe wasn't wasting any time. It was assembling its largest structures at breakneck speed. These early mergers operated differently than those we see today. With more gas available and fewer heavy elements polluting the mix, collisions triggered ferocious bursts of star formation, turning young galaxies into luminous beacons. The galaxy ZF Cosmos 20115, observed by Webb at just 800 million years after the Big Bang, reveals this perfectly. Its distorted shape and multiple bright knots betray the aftermath of a recent merger, with star formation rates hundreds of times higher than our Milky Ways. Such extreme starbirth was possible because the early universe's pristine gas lacked the dust and heavier elements that today help gas clouds cool and collapse more efficiently. Instead, mergers provided the necessary shockwaves to jumpstart the process. But the most surprising discovery is how quickly some galaxies grew. Webb's observations of the galaxy cluster SMACS 0723 include a massive galaxy that shouldn't exist according to older models. It's too big, too soon after the Big Bang. The likely explanation, a runaway series of mergers that allowed it to bulk up faster than theorists predicted. This challenges our understanding of galaxy formation, suggesting that early universe collisions weren't just common. they were staggeringly efficient at building giants. What's equally fascinating is how these ancient mergers set the stage for today's universe. The supermassive black holes lurking in modern galaxies likely grew during this chaotic period, fed by the gas funneled inward during collisions. The heavy elements forged in these early starbursts became the building blocks for future generations of stars, and eventually, planets like Earth. Even the vast voids and filaments of the cosmic web we see today were shaped by the gravitational echoes of these primeval crashes. As Webb and other telescopes continue to peel back the layers of cosmic time, each observation adds another piece to the puzzle. We're witnessing the universe's messy childhood, a time when galaxies grew not just by gently collecting gas, but through violent, transformative encounters that shaped everything that followed. And in those faint, redshifted images, we're seeing the origins of our own galactic home, built piece by piece in the fires of ancient collisions. When galaxies collide, they don't just rearrange stars, they forge the very elements that make up our world. The starbursts ignited by these cosmic crashes become factories for supernovae, those titanic explosions that scatter heavier elements like cosmic sprinkles across the interstellar canvas. Imagine a single dying star detonating with the brightness of a billion suns, hurling iron, gold, and uranium into the void. Now multiply that by thousands, all within a merging galaxy. This isn't just destruction. It's the universe's most extravagant recycling program, where the ashes of dead stars become the building blocks for new worlds. Take the Antennae galaxies locked in their fiery embrace. Hubble's images reveal not just swirling gas but pockets of intense radiation, the fingerprints of recent supernovae. Each explosion acts like a cosmic bellows, blowing enriched material outward at millions of miles per hour. Over time, these elements mix with surrounding gas clouds, seasoning them with the ingredients for rocky planets and even life. The oxygen we breathe, the calcium in our bones, the silicon in Earth's crust, all were forged in stellar furnaces and scattered by supernovae, many triggered by galactic collisions like these. But supernovae do more than just spread heavy elements. Their shockwaves ripple through galaxies like cosmic dominoes, compressing nearby gas clouds and triggering waves of additional star birth. It's a self-perpetuating cycle. Mergers create starbursts, starbursts spawn supernova, and supernova ignite more star formation. The tadpole galaxy's glittering tail showcases this perfectly. Its blue star clusters are likely the grandchildren of earlier supernova, their material recycled through multiple generations of stellar life and death. The timing of these explosions is equally fascinating. Starburst galaxies can produce supernova at rates hundreds of times higher than quiet galaxies like the Milky Way. In merging systems, astronomers might detect a new supernova every few months, compared to our galaxy's average of one every 50 years. This frenetic activity means colliding galaxies evolve at breakneck speed, their chemical composition changing dramatically within just a few million years, a blink in cosmic terms. Perhaps most remarkably, we can trace this enrichment process right back to the early universe. The oldest stars in our galaxy, found in its halo, contain barely any heavy elements. But younger stars, born after generations of supernova, are richer in metals, proof of how each stellar death paved the way for more complex chemistry. Galactic collisions turbocharge this process, concentrating supernova in space and time to create pockets of extreme chemical diversity. So the next time you hold a piece of jewelry or feel the weight of a coin, remember, the gold in your hand was likely born in the heart of a supernova, its atoms flung across space by a galactic collision billions of years ago. These violent mergers aren't just reshaping galaxies, they're crafting the raw materials of planets, oceans, and even life itself, one exploding star at a time. Deep in the final act of a galactic collision, when two supermassive black holes spiral toward their inevitable merger, the universe performs its most astonishing trick. It bends space-time itself. These cosmic behemoths, each weighing millions or even billions of times our sun's mass, don't just vanish when they collide. Instead, they unleash gravitational waves, ripples in the fabric of reality that race across the cosmos at light speed. Picture dropping two pebbles into a still pond. The circular waves that spread outward are a faint echo of what happens when black holes merge, except these ripples stretch and compress the very dimensions we exist in. The energy released in these mergers is beyond comprehension. In the last few seconds before collision, the orbiting black holes lose energy equivalent to the mass of several suns, converted entirely into gravitational waves. The resulting space-time tremors briefly outshine all the stars in the observable universe combined. Yet by the time these waves reach us, they've faded to near undetectability, distorting distances by less than the width of an atom. That's why detecting them required building LIGO and Virgo, instruments so precise they can measure changes 1,000th the size of a proton. When these observatories first heard the chirp of merging black holes in 2015, they weren't just confirming Einstein's century-old prediction. They were opening a new window into the universe's most violent events. But the supermassive black hole mergers at the hearts of colliding galaxies are different. These titans produce gravitational waves with wavelengths so long, spanning years instead of fractions of a second, that our current detectors can't hear them. That's where future observatories like LISA come in. This space-based laser array, slated to launch in the 2030s, will float millions of miles apart in orbit, forming a triangle sensitive enough to catch the low-frequency rumble of billion solar mass black holes merging. Imagine listening to the deepest notes of a cosmic symphony, vibrations so slow they take months to complete a single cycle. These waves will carry secrets about how black holes grow, how galaxies evolve, and perhaps even how space-time behaves under extremes we can't recreate on Earth. What makes these detections so revolutionary is their ability to reveal the unseen. Light from collisions can be obscured by dust or drowned out by brighter objects, but gravitational waves travel unimpeded. They'll let us peer into the chaotic moments when two event horizons finally touch a process where conventional physics breaks down. Some theories suggest merged black holes ring like bells, their vibrations encoding information about their shapes and spins. Others predict exotic phenomena like gravitational wave memory, where space-time permanently retains wrinkles from the collision. Each merger we detect adds another piece to the puzzle, helping us understand how galaxies like our own Milky Way and Andromeda will ultimately unite their black holes in an event that will shake the cosmos. The most thrilling possibility, these waves might already be washing over us. Right now, as you watch this, space-time could be stretching and squeezing imperceptibly from some distant galactic merger. Future observatories won't just study these events, they'll map them across cosmic history, building a gravitational wave background that whispers the story of how galaxies grew through collisions. It's a reminder that the universe doesn't just communicate through light and dust, but through the subtle warping of reality itself, a language we're only now learning to hear. Galactic collisions aren't just scientific phenomena, they're masterpieces painted across the cosmos, their swirling arms and radiant hues echoing the brushstrokes of Van Gogh's Starry Night. The Antennae galaxies, with their golden cores and sapphire star clusters, look less like astronomical objects and more like abstract art, a celestial Kandinsky where gravity replaces pigment. Artists have long drawn inspiration from these cosmic encounters, translating their chaos into canvases that capture the universe's raw creativity. Take the works of space artist Lynette Cook, whose paintings of colliding galaxies blend scientific accuracy with dreamlike wonder, or the psychedelic nebulae in Disney's Fantasia, which borrowed directly from Hubble's images of galactic mergers. Even film composers like Hans Zimmer have channeled their grandeur, scoring interstellar collisions with orchestral sweeps that mirror the slow-motion drama of stars being born and scattered. The allure lies in their paradox, destruction, and beauty intertwined. When galaxies merge, their violence births luminous starbursts, painting the cosmos in electric blues and fiery oranges. These palettes have seeped into Earth-bound art, from the neon nebulae of retro sci-fi posters to the iridescent swirls of modern digital installations. The pillars of creation might be iconic, but colliding galaxies offer something more dynamic, a snapshot of transformation, where every tendril of gas and every displaced star cluster tells a story of reinvention. Digital artists like Eric Wernquist use astrophysical simulations to animate these encounters, rendering them as swirling ballets of light and shadow, while photographers like Judy Schmidt stack Hubble data to reveal hidden details, turning raw science into visual poetry. Beyond traditional art, these cosmic crashes have shaped entire aesthetic movements. The Art Deco era borrowed their symmetrical chaos for geometric patterns, while VFX teams on films like Interstellar studied merger simulations to animate Gargantua's accretion disk with unnerving realism. Video games, too, have embraced their drama. The Destiny franchise's Dreaming City is a love letter to galactic collisions, its floating ruins and violet skies mirroring the ethereal aftermath of a celestial merger. Even fashion designers have woven their patterns into textiles, with constellations of sequins and silk mimicking tidal tails. What makes these collisions so artistically fertile is their universality. They're both myth and math. Ancient cultures saw them as gods clashing in the heavens, while modern astronomers decode their physics. That duality resonates. The same gravitational forces that sculpt galaxies into surreal shapes also stir human imagination, bridging the gap between equations and emotion. When a poet writes about stars colliding like lovers, or a filmmaker frames a hero's journey against a backdrop of merging spirals, they're tapping into a truth deeper than science, that the universe's most violent acts can also be its most beautiful. Every Hubble image of a galactic collision is a reminder creativity isn't just a human trait. It's woven into the fabric of space-time itself. Misconceptions about galactic collisions often paint them as cosmic car crashes, violent, fiery encounters where stars collide in spectacular explosions. The truth is far more elegant. Space is unimaginably vast, and the distances between stars are so enormous that even when galaxies merge, their stars glide past one another like dancers in an endless ballroom, never touching. Picture two flocks of birds flying through each other in slow motion, their paths intertwining but never clashing. That's the reality of galactic mergers, a graceful rearrangement, not a demolition derby. The real force at work here is gravity, not as a destructive wrecking ball, but as a patient sculptor. Over hundreds of millions of years, it gently tugs at stars and gas clouds, weaving them into new patterns. The Antennae galaxies, for instance, have spent 300 million years in a gravitational embrace, their long tails stretching across space like ribbons of starlight. Yet despite this dramatic reshaping, the stars within them remain unscathed, their individual journeys altered but unharmed. Even our own solar system, when the Milky Way collides with Andromeda, will likely continue orbiting the galactic center undisturbed, as if nothing has changed. Another common myth is that these collisions trigger rampant stellar explosions. While it's true that mergers can ignite starbursts, these aren't the chaotic detonations of individual stars. Instead, compressed gas clouds collapse under gravity's touch, birthing new stars in glowing nurseries. The tadpole galaxy's glittering tail, for example, isn't a trail of destruction. It's a ribbon of creation, dotted with young star clusters forged from the collision's shockwaves. Even supermassive black holes at the hearts of merging galaxies take their time, circling each other for eons before finally merging in a ripple of space-time rather than a cataclysmic blast. What's often overlooked is the sheer timescale of these events. Human lives are measured in decades, but galactic collisions unfold over billions of years. A single pass between two galaxies can last longer than all of recorded history, their shapes warping so slowly that no civilization would witness the full transformation. This glacial pace is why mergers appear serene in telescope images. We're seeing just a single frame in a cosmic film, playing at a fraction of a frame per millennium. So while the idea of galaxies colliding might sound like a recipe for chaos, the universe operates differently. These encounters are less about destruction and more about reinvention, a slow, majestic dance where gravity writes the steps and the stars follow in perfect, unhurried harmony. Hidden in the flood of data from modern telescopes lies a secret. Some of the most groundbreaking discoveries about colliding galaxies aren't made by professional astronomers, but by everyday people sitting at home with a laptop. Projects like Galaxy Zoo have turned cosmic exploration into a team sport, inviting volunteers from all walks of life to scan through millions of galaxy images, spotting the telltale signs of mergers, distorted shapes, tidal tails, or the eerie glow of colliding gas clouds. What began as a way to categorize galaxies has blossomed into one of astronomy's most unexpected success stories, proving that you don't need a PhD to contribute to our understanding of the universe. Take the case of Hanny's voorwerp, a bizarre green blob of ionized gas discovered by Dutch schoolteacher Hanny van Arkel while she was classifying galaxies on Galaxy Zoo. At first, astronomers were baffled. What was this glowing cloud, floating near a spiral galaxy like a cosmic ghost? Turns out, it was a quasar's echo, a relic of when the galaxy's central black hole was devouring matter so furiously it lit up the surrounding gas like a neon sign. Without an army of volunteers sifting through data, this celestial oddity might have gone unnoticed for years. The beauty of citizen science is how it taps into human pattern recognition, something our brains do better than even the most advanced algorithms. Computers struggle to distinguish between a galaxy gently warped by a nearby companion and one torn apart by a full-blown collision. But human eyes, trained by platforms like Galaxy Zoo, can spot the subtle differences in a heartbeat. Volunteers have identified rare polar ring galaxies where a ring of stars orbits perpendicular to the main disk, likely the aftermath of a cosmic sideswipe, and peculiar train wreck mergers with multiple galaxies tangled in gravitational chaos. What's truly revolutionary is how these projects democratize discovery. A retiree in Tokyo, a taxi driver in Buenos Aires, or a high school student in Oslo might be the first to flag a never-before-seen galactic interaction. Some volunteers have even co-authored scientific papers, their names listed alongside professional astronomers, proof that curiosity, not credentials, drives progress. Platforms like Zooniverse now host dozens of space-related projects, from hunting supernovae in galaxy mergers to mapping the gas filaments that connect colliding giants. The data deluge from telescopes like Hubble and the upcoming Vera Rubin Observatory makes this crowdsourcing essential. There simply aren't enough professional astronomers to analyze every image. But with millions of eager volunteers, the search for cosmic collisions becomes a shared human endeavor, stitching together a global tapestry of observers united by wonder. Every click, every classification adds another thread to our understanding of how galaxies dance, collide, and transform, one citizen scientist at a time. The next decade of galactic collision research isn't just about observing the cosmos. It's about decoding its hidden language with tools so advanced they'd seem like science fiction a generation ago. At the forefront is the Vera Rubin Observatory, poised to begin its legacy survey of space and time in 2025. This ground-based telescope won't just capture snapshots of merging galaxies. It'll create a 10-year time lapse of the sky, spotting subtle changes in colliding systems that reveal dark matter's invisible hand. Imagine tracking the warp and flow of tidal tails across centuries, or catching the flicker of a supermassive black hole duo as they inch closer. This survey will turn galactic mergers from static portraits into dynamic films, with gravity as the director. But the real game changer lies in AI's ability to sift through this avalanche of data. Machine learning algorithms trained on millions of simulated mergers can now spot patterns no human eye could discern. Researchers at the University of California recently developed a neural network that predicts how colliding galaxies will evolve by analyzing their shapes alone, like a cosmic fortune teller reading the twists of spiral arms. Other AI tools are decoding the faint gravitational lensing effects that betray dark matter's distribution during collisions, mapping its elusive contours with unprecedented precision. These digital assistants don't replace astronomers. They amplify their vision, revealing connections in data that would otherwise remain buried. Meanwhile, the upcoming Nancy Grace Roman Space Telescope will peer deeper into the infrared spectrum than ever before, cutting through the dust shrouds of merging galaxies to expose their fiery hearts. Its wide-field camera could catch the moment two supermassive black holes begin their final spiral, a phenomenon normally hidden behind veils of gas and stars. Combined with gravitational wave detectors like LISA, which will sense the low-frequency ripples from these colossal mergers, we're on the verge of witnessing black hole collisions in both light and space-time vibrations, a multi-messenger approach that could crack open general relativity's toughest puzzles. The most tantalizing frontier, simulating entire galactic collisions in virtual reality. Astrophysicists at MIT are already building immersive models where researchers can step inside a merger, watching streams of stars flow past like cosmic rivers. These aren't just visualizations, they're interactive laboratories where scientists can tweak dark matter ratios or gas densities on the fly, testing how subtle changes alter a galaxy's fate. It's like rewinding and fast-forwarding cosmic time with a joystick, uncovering the delicate balance between chaos and order that shapes the universe's grandest structures. What ties these advances together is their potential to solve galactic collision's greatest mysteries. How do mergers seed supermassive black holes? Can dark matter's properties be pinned down by studying how it behaves during collisions? And perhaps most profoundly, do galactic mergers follow universal rules, or is every encounter a unique cosmic snowflake? The answers won't just fill textbooks, they'll rewrite our understanding of how galaxies, including our own Milky Way, came to be. With each new tool, we're not just observing the universe's dance, we're learning its steps, one groundbreaking discovery at a time. Witnessing galaxies collide across the cosmos isn't just a scientific marvel, it's a humbling mirror held up to humanity's place in the universe. These cataclysmic events unfolding over eons underscore a profound truth. Our planet is a fleeting oasis in an ocean of cosmic chaos. While galaxies merge and stars are born from destruction, Earth's delicate biosphere hangs in a precarious balance, sheltered by nothing more than a thin atmospheric veil. The same forces that sculpt magnificent tidal tails and starbursts could, on our scale, render entire civilizations vulnerable to celestial threats like asteroid impacts or solar flares. This paradox, studying unfathomably powerful events while tending to our fragile home, frames one of space exploration's greatest ethical dilemmas. Consider how our view of galactic collisions has evolved. For centuries, astronomers saw them as distant spectacles with no connection to earthly concerns. But modern telescopes reveal these collisions as elemental forges, events that spread the very atoms composing our bodies across space. The iron in our blood, the calcium in our bones, were likely forged in stars ignited by ancient mergers. This cosmic perspective reshapes environmental ethics. If we're literally made of stardust recycled through galactic collisions, what responsibility do we bear for preserving the rare planetary conditions allowing that stardust to become conscious? The famed overview effect, reported by astronauts, the profound shift in awareness when seeing Earth from space, finds its scientific counterpart in astrophysics. Studying colliding galaxies doesn't just expand knowledge, it compels us to recognize Earth not as humanity's birthright, but as a temporary haven in a violent universe. Yet this awareness sparks difficult questions. Should resources devoted to studying distant galaxies be redirected to solving climate change or biodiversity loss? The answer lies in recognizing their interdependence. Technologies developed for space observation, from precision sensors tracking atmospheric changes to AI models predicting ecological tipping points, often become vital environmental tools. The Hubble Space Telescope's optics, for instance, inspired advanced air pollution monitors. More fundamentally, galactic research provides the long-term perspective our planetary stewardship desperately needs. By revealing how rare and fleeting habitable worlds are in a cosmos dominated by extremes, it strengthens the case for protecting ours. When astronomers estimate that Earth-like planets may exist in just one of every 5 colliding galaxy systems, spaceship Earth transforms from metaphor to urgent reality. The ethical dimension extends beyond preservation to exploration itself. As we develop technologies capable of altering celestial bodies, whether through asteroid mining or terraforming, we must ask, do we have the wisdom to reshape other worlds when we struggle to care for our own? The same gravitational physics governing galactic collisions also binds us to nearby asteroids rich in precious metals. Extracting these resources could alleviate terrestrial scarcity, but unchecked exploitation risks repeating Earth's history of environmental degradation on a cosmic scale. Perhaps colliding galaxies offer a model. Their mergers recycle material without waste, turning destruction into creation over billions of years, a lesson in sustainable cosmic engineering. What emerges from this ethical reflection is neither pessimism nor hubris, but perspective. Galactic collisions teach us that change is the universe's only constant, yet also reveal the extraordinary rarity of conditions allowing life to witness that change. This duality should guide our actions, pushing boldly outward to understand the cosmos while nurturing our planetary lifeboat with unprecedented care. After all, the light from colliding galaxies shows us the past, but in protecting Earth, we're shaping a future where such cosmic wonders remain visible not just to our telescopes, but to generations of curious minds yet unborn. Galactic collisions are more than cosmic accidents. They're the universe's way of creating, destroying, and reinventing itself. These celestial encounters are the architects of the cosmos, shaping galaxies into spirals, ellipticals, and irregular forms with a creativity that surpasses even the wildest human imagination. Every time 2 galaxies intertwine, they rewrite the rules of their existence, transforming chaos into something breathtakingly new. The Antennae galaxies, with their star-studded tails, and the Cartwheel's perfect ring, are testaments to this endless cycle of destruction and rebirth, proof that even in the vast emptiness of space, nothing remains static. At the heart of these collisions lies a paradox. The same forces that tear galaxies apart also seed them with new life. Starbursts ignited by colliding gas clouds forge generations of stars, while supermassive black holes, drawn together in a gravitational waltz, eventually merge in a ripple of spacetime itself. These events aren't just spectacles, they're the engines of cosmic evolution, recycling matter and energy on scales so vast they defy comprehension. The Milky Way's own history is written in the remnants of past mergers, and its future will be defined by its dance with Andromeda, a collision that will reshape our night sky into something unrecognizable yet no less magnificent. What's truly humbling is how these collisions connect us to the universe. The atoms in our bodies, the iron in our blood, the calcium in our bones, were forged in stars born from ancient galactic encounters. We are quite literally the products of cosmic violence transformed into something capable of wonder. When you gaze at the stars, you're not just looking at distant lights, you're witnessing the aftermath of collisions that occurred billions of years ago, their light finally reaching us as a whisper from the past. As our understanding deepens, so does our appreciation for the universe's grand narrative. Telescopes like Hubble and JWST have peeled back the veil on these cosmic dramas, while citizen scientists and supercomputer simulations help decode their secrets. Yet for every question answered, new mysteries emerge: dark matter's invisible hand, the fate of orphaned stars, and the true scale of the universe's recycling program. Each discovery reminds us that we're part of a story much larger than ourselves, one where galaxies collide not as endings, but as new beginnings. So the next time you step outside and look up, remember, the night sky is a living, changing canvas. Those stars, those galaxies, even the spaces between them, they're all participants in a cosmic ballet that's been unfolding for billions of years and will continue long after we're gone. If this journey through the art of galactic collisions has sparked your curiosity, share your thoughts below. What fascinates you most about these cosmic encounters? And don't forget to subscribe for more explorations into the wonders of the universe. The cosmos is vast, mysterious, and endlessly surprising. Let's keep uncovering its secrets together.